network is down again.
Network is down again.
Yeah.
Hello, hello.
The recording team is ready. Okay. Yeah. Okay. Thank you. Good morning. So let's continue our discussion on spintronics. Okay. So today we are going to learn about the origin of spintronics and the first application of spintronics. Okay. So as usual, we'll have OCLAB session. So please scan the QR code and log in to OCLAB. And I also want to make this announcement on the Friday 23rd May afternoon you will have exam. Okay, so this is part of the course. So the exam will be of 2 hours. So there will be multiple choice questions. So there will be only one right answer. Okay. So if there are A, B, C, D options, just choose one right answer. Then Saturday the last session will be, we will be discussing those questions. I think that also will help me how much you have understood. So I can revise those part and we can reinforce those concepts that you didn't learn very well. Okay. Okay, so this is how it will be happening. Yes, I will give you like 30 more seconds to scan the QR code. Okay, so let us get into the topic today. So, first slide itself is a question. Okay, so before I discuss the answer for this question, let us go to the next question. Okay, so now we go to the first question. Okay, so this is very quite expected because I didn't teach you. So all of you are guessing, right? Okay, not this is the not. This is the first question, for which we have given various answers. So, I have mentioned many times that hard disk technology is the one which gave rise to the Spintronics principles. Okay? And hard disk technology is the first technology to use Spintronics principles, and hard disk technology typically generates $20 billion per year. Okay? So, the correct answer is like, let us say we just exclude whatever MRAM brings in. So, it is about $20 billion per year. So, this is the kind of impact that Spintronics has on the economy. For the next question, you should know like how long we have been using Spintronics principles. Okay. So, Spintronics technique has been used for around 25 years. Okay. This slide was prepared, I mean this question was prepared 5 years ago. So, assume 20 years multiplied by $20 billion will be 400 billion. Okay. So, this is the correct answer. So, basically these slides tell you that Spintronics is not something very new. Okay. So, for some of you, you may think that Spintronics is very new, but Spintronics has been there even before people coined the word Spintronics. Okay. So, some of the concept that I will teach you happened in 1980s, and some of the concepts have happened like even in 1800s. Okay. So, at that time we did not have the word Spintronics. So, Spintronics is not very new, and it is not like a blue sky topic, it has applications. Okay. So, it already has applications in as a read sensor in hard disk drive, and MRAM is a new application. Okay. So, today we will be learning about how we can sense information using Spintronics principle. So, this is some slide that I gave you on the first day. I told you that in conventional electronics we only utilize the charge property of the electrons, because all the elements in the conventional electronics are like silicon, copper wiring and so on, which are based on non-magnetic materials. On the other hand, in Spintronics we will be using magnetic materials. So, we are going to use the spin property of the electrons. Okay. So, when you have magnetic materials and you send electrons through magnetic materials, there is the interaction between the spin and the magnetization of the magnetic material. As a result, the electron flow will be spin dependent. Okay. So, we are using this spin dependent property in Spintronics. Okay. So, this is something that I introduced on the day 1. Okay. So, I told you that Spintronics has been used for around 25 years now. So, if Spintronics wasn't there, for example, the hard disk that you buy may have a capacity of 100 gigabyte. Okay. Now, you are easily buying 10 terabyte, but if Spintronics wasn't there, maybe like 50, 100 gigabyte or so, okay, not more than that. So, hard disk drives would have a very low capacity. So, probably we will be still using DVDs to store information, or flash memory would have taken, and we would have no application like YouTube, Facebook, things like that. And more importantly, all those movies that you see with a lot of computer graphics would not be possible. Okay. So, to give you one example, James Cameron made Titanic movie in 1997. So, at that time itself he had the concept of Avatar. Okay. So, 1997, from 1997 until 2009 he did not release any movie, okay, around 12 years. So, he was waiting for this Avatar movie to be made, because the technology was not ready. Okay. So, to give you a reason why, for example, so when you shoot movie, you generate lot of digital data. So, I told you that if you shoot movie in certain format, you need so much terabyte per hour and things like that, right. So, to shoot a movie like Avatar, you need like 1 to 2 petabytes of information. Okay. So, you need hard disk drives with this kind of capacity. So, in 1997 the highest capacity of the hard disk drives was like only 500 megabyte. Imagine, it is not even 500 gigabyte, 500 megabyte was the typical capacity. So, around 2006-7 at that time we could make like 300-400 gigabyte hard disk drives. So, storing lots of information in 1 petabyte was possible only around 2007. So, that is about storage. Then we also need to talk about memory and so on. So, all those technologies were not ready to make a movie like Avatar, and only like 2007 or so hard disk drives were enough to shoot movies like this. Okay, now we have an overdose of CGI movies. I hate, they do not have any storyline, just all nonsense. Okay, so this is also another impact of Spintronics. So, if Spintronics was not there, maybe probably we would not have all those Marvel, DC movies. Okay. So, it is also good to know how the technology and science progress hand in hand. So, science is like a tree which bears the fruit. Okay. So, scientific discovery, let us say scientific discovery is a seed. Okay. So, it takes time to grow and give fruit. Okay. So, fruit we can say is a technology. Okay. So, you can see here the scientific discovery and the technology, how and when happened, when it happened. So, we can see, for example, in the 1800s people were studying electricity. So, they knew that charges are responsible for electricity, but they did not know about electrons. Somewhere in 1900s electrons were discovered. Then people used these electronics, I mean they started building electronics. So, the first electronics was based on vacuum tubes. Okay. So, they have a tube with anode, cathode, grid and so on. So, they could control the flow of electrons. Then we had vacuum tubes. So, these vacuum tubes were very useful in the World War I, II and so on. Okay. So, this is like when electron was discovered and when they were like used really. Then if you take spin, for example, the concept of spin happened somewhere in 1925. Then people came up with some theoretical model, and one of the discovery based on spin was giant magnetoresistance. This happened in 1989, and after 11 years people could make some sensors based on the giant magnetoresistance, and they can use it in hard disk drives. So, since 2000 we have been using, I mean even before that we have been using some Spintronics heads for reading information. That is one thing, that is about spin. Then there are some concepts that you will learn later, spin transfer torque and so on. So, this spin transfer torque was discovered in 1996. Okay, so, 1996 spin transfer torque was discovered, but people started using this concept for technology somewhere around say 2018. So, around 20 years it took to make use of this discovery. Then around 2012 there are a lot of research papers on spin orbit torque. Okay. So, this has not yet made into a technology, spin orbit torque is not yet a technology, but it is going to be useful somewhere in the future. So, you can see that the discovery happened sometime, then at some point of time some technology comes into picture. Okay, so, here I will say the story of Spintronics. So, in the late 1800s, late 19th century. So, people thought that everything in physics has been done. Okay. So, the Newtonian mechanics was there, then Maxwell's laws were there. So, people thought that they understood everything. So, it was said that Lord Kelvin he even mentioned that there is nothing in physics to be done, only some fine tuning of physics we need to do, something like that. Okay. But you know that in early 1900s, so many new observations were coming, black body radiation, spectroscopy, so many things came at that time that led to the revolution called quantum mechanics. Okay. So when you talk about spectroscopy, it was coming into picture. So people were expecting, say for example, spectral lines at this position 1, 2 and 3. This was supposed to be the theoretical spectral lines, but when you do experiments, people observed that there are some fine splitting. Okay. So instead of one line here, they saw two lines, again instead of one line they saw two lines and so on. Okay. So there are some fine splitting happen in the spectral lines. So experimentalists blamed that this is theoreticians blamed the experimentalists. They said this is experimental error, this is not possible. However, this guy Goldsmith, okay, by the way, you go to this website, you can look at his lecture. Okay. So he has a talk which is like a story of how he came up with the concept of spin. Okay. So in that lecture he tells that before even he knew these results, he had done some calculation and he came up with the concept of spin. But once he saw these results, then he realized that his derivations fit into this picture very well. Okay. Then he discussed with another colleague called Goldsmith and another one who is that Uhlenbeck. Okay. So this Uhlenbeck is the one who gives the name spin, and he, according to Uhlenbeck, he says that electrons have some angular momentum, electrons are spinning, and he proposed, these two together propose this and get it published. Then people didn't believe. So because electron cannot rotate, because electron's rotation will be violation of the physical laws. So people didn't believe, but at around same time this Stern-Gerlach experiment happened. Okay. So before I explain this Stern-Gerlach experiment, so I want you guys to do one experiment. Okay. So here I have a fidget spinner. Okay. So this fidget spinner, see, I can easily flip. Okay. Okay, I challenge you. You rotate the fidget spinner like this, then try to flip. Rotate very fast. Stand up, come here. Rotate very fast. It's not enough. No, rotate very fast. Okay. Okay. So I can easily flip, right? But he cannot flip. Why? Yeah? Angular momentum. Okay. So when I flip, this fidget spinner doesn't have angular momentum, but when I rotate, there is an angular momentum, say either pointing this way or the other way. So when there is an angular momentum, you need a huge torque to change the angular momentum of this spinning object. Okay, with our wrist power, we cannot provide that much torque, so we cannot change the angular momentum. So let us say even if you hold the fidget spinner like this, you try to change the direction. Say, tell me what you feel. Rotate very fast. This speed is not enough. Do you feel something?
Slightly.
Okay, someone else try. What do you feel?
It's not as easy to just
What do you feel?
It's somewhat difficult. But
Yeah, you will feel some force on your thumb because you are changing the angular momentum. So, there is a torque, I mean by equivalent version of Newton's third law of motion, there will be, you will feel a kind of force on your fingers. Okay. So, what this whole experiment tells you is that if something has angular momentum, it is difficult to flip. If there is no angular momentum, it can be easily flipped. Okay. So, having known this concept, now let us get into this Stern-Gerlach experiment. Okay. So, in this experiment they are sending electrons through two magnets, I mean two poles of a magnet. These poles are designed in such a way that the magnetic field lines are more in one pole. Okay. So, you see that the magnetic field lines go from this pole to the other pole. You can notice that the field lines are more here, right. So, if you count the number of field lines in this area, you will find more lines. The same you find here, you will find less line, which means the magnetic field is larger here and less here. Okay. So, let us say you send electrons, and if electrons are only magnets, so if you remember on the day when we learnt magnetism, I told you that electrons are like tiny magnets. Okay. So, if electrons are like only tiny magnets, when you send them through this. So, let us say this is north, there is one electron going with the south pole here. Okay. When it comes in this vicinity, it will rotate, the south pole will go and stick here, because the magnetic field is strong here. So, all the magnets will be attracted here. Okay. And if electrons are only magnets, just magnets without spin, for example, then they will just rotate the pole and they will finally reach here. So, you will see nothing here if you think electrons are only magnets with no angular momentum. Okay. On the other hand, experimentally they found that there are electrons in both directions. Okay. There are some electrons in this region, some electrons in this region, and this concludes the point that electrons have angular momentum. Okay. So, let us say electrons have angular momentum, like this fidget spinner we could not flip, right. When the fidget spinner was rotating, we could not flip. So, they have angular momentum. So, this, let us say I told you in one case, for example, this south pole will flip and go here, that cannot happen because they have an angular momentum. So, they cannot flip with this kind of force. So, they will still continue to go along this direction. So, because of the angular momentum nature of electrons, you will see electrons in both sides. So, you will see two patterns corresponding to spin up and spin down electrons. Okay. So, this is what they observed in the Stern-Gerlach experiment. So, they saw electron pattern on two direction, indicating that electrons have spin. Okay. So, why electron cannot spin is like when you are talking about spin, for example, this fidget spinner, right, there is a center, and outside this center there are so many tiny particles, right. So, because of that we can have some spin, angular momentum, but electron itself is a fundamental particle. So, it cannot rotate around its own axis and so on, and again the speed of rotation will exceed the speed of light and things like that. Okay. So, that is basically a very brief introduction to spintronics. Now, we move on to learn how we can use these Spintronics principles to sense information. Okay. So, you would have learnt about many types of sensors. So, what does sense mean? So, in electronics, sensing means knowing, converting a physical property in the form of an electrical current or voltage. Okay. For example, if you take a digital thermometer, so in the case of a digital thermometer, you may have some resistor, let us say platinum resistor. So, this resistance will change as a function of temperature. Okay. So, you keep the thermometer at certain temperature, say T1, the resistance will be R1, T2 the resistance will be R2, T3 resistance is R3, and so on. Okay. So, by knowing the resistance, by measuring the resistance of this element, we can convert resistance into temperature. Okay. So, there again you are measuring the resistance because you are sending a current and measuring the voltage. Okay. So, sensing is basically converting a physical property into an electrical current or voltage. Okay. So, in the case of magnetic recording, we learnt yesterday that the magnetic media produces magnetic flux, and we are sensing this flux. Okay. Flux or magnetic field, you can say magnetic flux or magnetic field. So, we are converting this magnetic field or flux information into some form of voltage. Okay. So, that is what the sensors in hard disk drive does. So, it converts the magnetic field or flux line information into voltage. Okay. So, in a hard disk drive you have many disks and the disk is rotating, and here you have some sensor. So, this sensor flies over the disk medium. Okay. So, we learnt that this kind of north facing each other will produce some magnetic flux and so on. So, this sensor will convert those magnetic flux lines into voltage. Okay. Based on some principle, you will get voltage pulses as a function of time. Okay. So, the flux that comes from the recording media is converted into voltage. So, that is what the sensors that we are going to learn are doing. Historically, the sensors for hard disk drives were based on the Faraday's law of induction. Okay. So, when we learn about VSM, okay, here we can say Faraday's law. So, when we learnt about VSM, vibrating sample magnetometer, I told you that if there is a time varying flux and if there is a pickup coil, the pickup coil will pick up a voltage which is proportional to the time varying flux. Okay. So, this is something that we learnt already. So, until 1990s we did not use Spintronics principle. Okay. So, we use this simple Faraday's law to sense information. Okay. So, forget about this for the time being. Okay. Just look at this one. So, this is an electromagnet. by sending current through this, we produce some magnetic field and we use this head for writing information. Okay. So, you can see that the material is magnetized in this direction or in the opposite direction by changing the current direction of this electromagnet. Okay. So, this is the writing element, and until 1990s people use the same writing element for reading also. Okay. So, for example, if you look at this as a pickup coil. Okay. So, this pickup coil will convert the time varying flux into a voltage. So, you can use, if you connect some voltmeter here and if you move the disc media below this, you will see voltage signals. Okay. So, we use this Faraday's law to read information until 1990s, but that was like there were many problems. For example, we learnt yesterday that MRT is responsible for signal, right. MR is the remnant magnetization, T is the thickness of the film. So, the product of these two gives rise to signal. So, you might say that if you increase this, you can increase the signal. Okay. That is a very simple thinking, but there are other problems. I did not go through the details yesterday. For example, if you make the MRT very large, the pulse width also is going to be very large. Your pulses will be very large, which means you cannot pack information at high density. So, pulse width, if your pulse width is large, your density will be low. Okay. So, to understand this one, let us recall the cheat sheet example. Okay. So, in your exam you can take a cheat sheet. So, you want to write the material for the exam. So, which pen will you use? You will use a pen with this kind of tip or sharper tip? Sharper tip, right. So, with sharper tip you can write fonts, small fonts. Okay. So, small font is like having very small PW50, a tip like this will produce very big letters, which means large PW50. So, we do not need a large pulse width, we need smaller pulses, but with large MRT you will have large pulses. So, you cannot achieve high density. With large MRT you can have high signal. Okay. So, people do not go to increase MRT, they try to reduce MRT to make the pulses narrower like this. They want sharper pulses. So, they can pack density, I mean information at high density. So, the problem of these inductive sensors were they did not get sufficient signal. Okay. So, when your MRT is low, the flux that you send out will be low. So, it is like if you have a big magnet, it will send more flux line at certain distance, but if you have a small magnet, the let us say here, for example. So, at certain point you will see more flux lines, whereas this will give only a few lines. Okay. So, when MRT was reduced, these inductive heads did not produce sufficient signal because the flux lines which were reaching this head were fewer. Okay. So, that was a problem, but hard disk drive was driving, I mean it was going smoothly until 1990s with this technology. Okay. Then in 1990s hard disk drive started using something called anisotropic magnetoresistance based heads. Okay. then at that point of time the reader was separate, I mean there was a separate read sensor and they had a separate write sensor. So, writer. Okay. So, that is what is shown here. So, here now after this discovery of anisotropic magnetoresistance, after introducing anisotropic magnetoresistance, people had one sensors based on anisotropy magnetoresistance for sensing and another writer. Okay, so, we can say that from 1990s the heads used in the hard disk drive have two parts. Okay. One part is for reading information, another part for writing information. Okay. So, this is the configuration we use since 1990s. Okay, so, one set of researchers focus on how to improve the writer and another set of researchers focus on improving how we can improve the sensitivity of the readers and so on. Okay. So, this is a real life chart of how technology has produced and what were the contribution of Spintronics, for example. Okay. So, until here people were using the inductive head. So, I told you that we have been using inductive heads since until 1990s. So, the growth was like 25% every year. Okay. So, for example, if I have 1 gigabyte this year, next year will be 1.25 gigabyte and so on. Okay. So, 25% increase every year until 1990. Okay. So, this is the year the industry used first magnetoresistive head. Okay. After they introduced the magnetoresistive head, you can see that the growth has increased to 60%. Okay. That means, if the capacity was 1 gigabyte earlier year, now we will have 1.6 gigabyte. Okay. You can see the difference. Then at some other point of time, say around 2000, people introduced GMR head. So, you will learn all this terminology later, but I am just giving you some data. After you introduce GMR head, you can see that the growth is 100% every year. Okay. So, for example, if the capacity was 10 gigabyte this year, next year it will be 20 gigabyte. Okay. It has almost doubled. Then later it will be 40 gigabyte. So, after people introduced the GMR head, the capacity was doubling every year. Okay. So, this is the impact of Spintronics in the hard disk technology. Okay. By bringing in Spintronics based sensors, we have improved the sensitivity of reading information. So, we could double the capacity for many years. Okay. Every year we were doubling for many years. So, these are the impact of Spintronics. Okay. So, now let us move on to learn about the, I keep saying AMR, GMR and so on, but we haven't learned what is magnetoresistance, right. So, we will start in a simple slide. So, you take a piece of wire, you apply some electricity, then you will notice that the electrons move from one side to the other side depending on the electric field you apply. Okay. So, the tiny particle that you see are the electrons. So, you can see that they drift. Okay. So, here I want to ask you this question. So, I am saying a snail may travel faster than electric current in a wire, copper wire for example. True or false? Okay, majority of you are right. Okay. Snail may move faster than a current in a current carrying wire. Okay. So, what happens when you have a conductor like copper, for example, you do not apply any electric field, you do not apply any voltage. Then what happens is that the electrons inside the copper wire, they will undergo random thermal motion. Okay. So, they will go from so, electron is here, it may go here, 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 something like this. It will undergo random motion, but the center of if you take the average position is somewhere here. Okay. So, with respect to this position, it is going here and there. So, typically this kind of random motion happen because of the collision of electron with say some phonon, scattering from phonon defects or other electrons causes this kind of phenomenon, and the typical distance before it undergoes a collision is around 1 to 10 nanometer. So, the mean free path of electron is around 1 to 10 nanometer. So, this is important, you note this point. Okay. And when you have like only the temperature effect, the typical velocity of these electrons is around 10 power 6 meter per second. Okay. Now, let us say you apply certain potential. Okay. So, you apply electric field, then again the electrons undergo this scattering. Okay. All these things still happen, but because of this electric field it is drifting. So, here the center was at one position, average position was somewhere here, but when you apply electric field, the average position moves from this point to this point, but still the electron is undergoing all this scattering. Okay, it slowly drifts. So, this is what we call drift velocity. So, typical drift velocity of electron is around 10 power minus 3 meter per second. Okay, it depends on the current density that you apply and so on. So, if you look at the speed of a snail is 13 centimeter per second, and the drift velocity for this will be actually very low, around 0.5 millimeter per second. If you apply very high current density, yeah, you can make the electrons move faster, but for typical current densities, the speed of electron along this direction can be lower than the speed of a snail. Then you may wonder, how come we switch on the switch and we can get the light immediately? The electricity appears to travel faster, right? So, for that you can take a water pipe analogy. Let us say you are living in your home and you have been living there for many years. Okay. So, you open the tap, you will get water immediately. Okay. On the other hand, let us say you move to a new house, you have a water tank on top of your house, water tank just got filled, then you open the tap in your kitchen, then you will realize that the water takes some time to reach. Okay. It has to travel all the way through the pipe, then it takes some time to reach you. Okay. On the other hand, if the pipe is already filled with water, the moment you open the tap, you will get the water immediately, right. So, in a similar sense, you can understand that the copper wire is filled with a lot of electrons. Okay. So, it is like a filled water pipe. So, your copper wire has a lot of electrons already. So, once you apply electric field, these electrons move here and these electrons move here and so on. So, you will notice that the electricity travels faster. Okay. Anyway, the most important part of this slide is that when electrons travel across a conductor, you can see that the electrons get scattered, and the resistance of material is caused by the scattering of electrons. Okay. So, how can you measure resistance? You can use a few techniques like 4 probe technique or Van der Pau techniques. So, in a 4 probe technique, let us say this is the material we want to measure. So, we have 2 probes through which we send current. Okay. So, electrons flow and we measure the voltage somewhere in between these 2 points. Then we divide the voltage by current, we get the resistance. Okay. So, this is how we measure resistance. And when you talk about magnetoresistance, what we do, we measure the resistance of a material at various values of applied magnetic field. Okay. So, you apply different magnetic field, for example, no magnetic field, you get some data. You apply say 1 Tesla, you get some data. So, like that you keep changing the magnetic field, measure the resistance of the material, then you notice that the resistance depends on the applied magnetic field. Okay. The resistance of the material that you measure depends also on the magnetic field. Okay. So, this kind of change of resistance of a magnetic material as a function of a magnetic field is called magnetoresistance. Okay. So, this is what you are going to learn. So, today I will not go into the theory. Today I will focus on how we can use the principles of the AMR, GMR and TMR, how we use them for reading information. Okay. So, the first topic that we are going to learn is anisotropic magnetoresistance or AMR in short. Okay. So, we learnt, I mean you are familiar with this word now, right. You know what is anisotropy now. Anisotropy means you measure certain property, the property is different in different directions. Okay. So, when we talk about anisotropic magnetoresistance, we are going to talk about some form of magnetoresistance which depends on the direction of something. Okay. What is the direction that we are going to talk about here, that is shown here. Okay. So, in this case we are going to talk about the direction or the angle between the magnetization and the current. Okay. So, we are applying current in the x direction. Let us say your magnetization is at certain angle theta with respect to the current. Okay. Then the resistance you measure will be different depending on this theta. Okay. So, if magnetization is in the same direction as current, you will have one value. If magnetization is perpendicular to the current, you will have another value. Okay. So, here the resistance is anisotropic based on the direction of magnetization with respect to the current. Okay. So, in the first case, magnetization is parallel to the current. So, we call this rho parallel because magnetization and current are parallel. So, we call it rho parallel. So, when these two are parallel, the theta is 0. So, you notice here that when theta is 0, the resistance is high. Okay. In the second case, the magnetization is transverse or perpendicular to the current. So, we call it rho perpendicular. So, rho perpendicular is like the angle is 90. So, here we have rho perpendicular, and for intermediate values of theta, your resistance is somewhere between this high and low. So, if you plot the resistance of this particular, so here we are talking, I mean this blue is a magnetic material. Okay. So, I do not need to say, but I will still say. So, the blue color material is a magnetic material, and we are looking at the direction of magnetization with respect to the current direction. Okay. So, if I measure the resistance of this magnetic material as a function of theta, where theta is the angle between current and magnetization, I will have this graph. Okay. So, when the current and magnetization are parallel, resistance is high. When the current and magnetization are perpendicular, resistance is low. Then for intermediate values, you have certain property like this. Okay. So, here this graph is normalized by dividing by the perpendicular resistance. Okay. So, the absolute values may be like, let us say this may be 600, something like that. Okay. This may be 500, something like that. The absolute values of resistance may be like 600 ohm here, 500 ohm here, but this graph is plotted by dividing all the data by this value 500. Okay. So, that is why you have a graph which goes from 1 to 1.02, something like this. Okay. So, from this measurement we can also define a parameter called AMR coefficient. So, AMR coefficient is the difference between the high and the low resistance. So, for example, 600 minus 500 divided by the low resistance, okay, 500. So, this will be 100 by 500, something like 0.2. Okay, so, these values are rubbish. Okay, do not take these values for granted. So, typically this change is only like 0.02. Here I have exaggerated too much. So, this delta rho for the best material is only around 2%. Okay, so, in terms of percentage it is only 2%. So, it is like this 0.2 is 2%. Okay. So, these values are not very correct, but I am giving you just for some understanding.
Sir,
yeah.
What is the origin of this difference of resistance between two companies?
Okay. For the AMR, right? The theory I am going to cover another day. Yeah. So, today I will focus on the how we can make use of this principle. Okay. So, this is an experimental result from our lab. So, in this case we have a wire, you can see that there is a wire of permalloy. Permalloy is an alloy of nickel and iron. Okay. So, on this wire we send current through this wire and measuring the resistance. Okay. By applying, okay, this is the wire, right. So, if I do not apply any magnetic field, where will the magnetization point to? Yeah, the magnetization will point along this direction. Why? Because of shape anisotropy. Okay. So, this is a narrow wire. So, you know that in narrow wire the easy direction is along the length. So, in the absence of magnetic field, magnetization will point in this direction. So, when the field is 0, magnetization is parallel to current. Okay, so, we know that when magnetization is parallel to current, the resistance will be high. Okay, so, we just learnt that when the magnetization is parallel to, so this theta is 0, resistance will be high. Okay, so that is what you see here. Now, let us say I apply magnetic field along the direction of current. Okay. So, my magnetic field also is along this direction. So, if I increase or decrease, so either I am going to make the magnetization along this direction or in the opposite direction. So, in all the cases the magnetization is going to be always along this line parallel to the current. So, when I measure the resistance of this device, when current is parallel to field, this value is very high. Okay. Because the magnetization is either pointing along this direction. If I apply magnetic field along the opposite direction, it will flip to the other direction. So, current and magnetization are always 0. So, the resistance is always high. So, that is what you see in the blue curve here. Okay. So, this line is basically when the field is parallel to the wire. Okay, now let us consider the other case when the field is perpendicular to the current direction. So, in the absence of any field, magnetization is in this direction, resistance is high, but once I apply magnetic field in this direction, magnetization will rotate along this direction. Okay. So, we learnt that when the magnetization and the current are perpendicular, okay, when the magnetization is perpendicular to the current, the resistance will be low. Okay, so, once I increase the magnetic field, I am tilting the magnetization from the easy direction to this direction of the applied field. So, the resistance drops. Okay. Okay, so, this is what happens when you try to measure the magnetoresistance of a material as a function of magnetic field. You can change the magnetization to be either parallel to the current or perpendicular to the current. So, in this case the magnetic field changes the magnetization direction from easy direction to the hard direction and so on. So, we see changes in the resistance. Okay. Yes. Okay. Will the wire not be in demagnetized state without applying any field? Yeah, possible. In the demagnetized state also, still the magnetization will be like parallel to the, I mean you may have domains. So, some domains magnetization will be like this. Okay. So, you will have different directions, but still magnetization is parallel to the current. So, you will have high resistance. So, your demagnetized state will be still like this. Okay. Something like this. So, again you can say that all these magnetization are parallel to the current direction. So, the resistance will be still high. Okay, this slide explains why, how, we will discuss this later, but now we will move on to learn how we can make use of this principle, anisotropic magnetoresistance, for sensing information. Okay, so, for sensing information you need, okay, the best material for anisotropic magnetoresistance is permalloy. Permalloy is an alloy of nickel and iron. So, typically 80-20 somewhere there. Okay, there will be some changes in the composition, but somewhere there. So, this is the best material. So, if you want to make a reed sensor based on anisotropic magnetoresistance, so what you will do, you will make permalloy wire patterned into some shape like this. Okay. So, the shape of the AMR element here will look something like this. Okay. Then you have two probes. So, you send current through the probes, then you measure the voltage. Okay. So, you use these two probes for measuring the resistance of this AMR element. Okay. So, as we just saw in the previous graph, when there is no magnetic field, magnetization is along certain direction, but when there is a magnetic field, the magnetic field influences the magnetization direction. So, there will be a change in the resistance, and we are using that change in the resistance to sense information. Okay. So, later I will ask.
आपको महंगा मिलेगा क्योंकि वो बहुत ऊपर है, तो आपको 4045 मिलेगा.
Not here, right? Okay. So, later I will discuss you exactly what angle will I will ask you some question later. Basically, you have a sensor, you have a MR sensor, anisotropic magnetoresistance sensor, and it sees some magnetic flux. The magnetic flux is coming from the recording media, and this magnetic flux changes the magnetization direction. As a result, you will see some change, and that is what you are going to read as information. Okay. So, when people design AMR head, they place this AMR element between two shields. So, you can see that there is one shield here, then there is another shield here. So, these shields are soft magnetic materials. Okay, so, these soft magnetic materials have a property of permeating all the magnetic flux into them. Okay. So, let us say if you have a magnet here, right, magnet here, this magnet produces certain magnetic field. Okay. So, in the absence of any other material, the magnet of the magnetic field of this magnet will look like this. Okay. On the other hand, if I place a soft magnetic material here, so all these flux lines will go through the soft magnetic material. Okay. So, this is what we learnt before briefly, not much. I mentioned the term permeability. So, soft magnetic materials have a tendency to collect all the magnetic flux through them. Okay. So, that is what the shields do here. So, look at this picture. So, here you have the recording media. So, you have written bits. So, some of them are pointing left, some of them are pointing right and so on. Okay, so, here you see there are two like poles. So, they produce some magnetic field. Then here again you have two like poles, there is some magnetic field. Here again you have two like poles and so on. Okay. So, there is magnetic flux lines coming out from many different bits. Okay. But you want this sensor to read the bit directly below it. Okay. You do not want this sensor to respond to the neighboring bit. Okay. So, what we do? We pass all this magnetic flux from the neighboring bits into the shield. Do you understand? I do not know if you get it or not. Okay, we have lot of bits. Okay. Let us say there is one bit here, it produces certain magnetic flux. There is another bit here, let us say this one, we have 0, no flux, 1, there is another 1. Okay. So, we have a lot of bits. So, from this region we have magnetic flux coming out. Okay. So, now my reader is coming, let us say the reader is supposed to read this bit. Okay. So, when you want this reader to, this is a AMR reader, when you want this reader to read this particular bit, it should not see the magnetic flux from the neighboring bits. Okay. So, we do not want this to interfere when it reads this bit. Okay. So, what we do? We do not let this field come here. So, we let this magnetic flux go through this shield. So, this shield basically sucks all the magnetic flux into it. So, none of this magnetic flux go into this region.
What is the typical distance between those two seals?
Pardon?
Those two seals.
Uh-huh.
The typical distance between those two.
What is the distance between these two shields, right? In some of the technology 10 years ago, maybe around 30 nanometer. So, it is very narrow.
At that time, the bit size was same 12 to 13 or more than that.
Yeah, around that. Bit size, when the bit size is around 30 nanometer, we have this kind of spacing. Yes.
So, bit size will always be the distance between two seals will always be smaller than the bit size.
Somewhere there, almost similar kind of thing.
So, if the bit size is smaller, then they can detect two bits at a time.
Yeah, yeah. So, if this is very large, right, let us say this is 100 nanometer, then you cannot read 15 nanometer bits. So, if you want to read 15 nanometer bits, you have to make them closer, like at least around 20 nanometer or something like that. Okay, so, the purpose of the shields here is to minimize the influence of the magnetic field from the neighboring bits. So, because of these shields, nothing comes to this region except the field from the bits directly below. Okay. So, as an analogy, you can say that this is like the blinder we use for horses. Okay. So, horses have blinders, right? They do not see this side or this side, they only see straight. So, in a similar sense, this MR sensor only sees the magnetic flux directly below it, not from the neighboring bits. Okay, but this technology did not last long. So, it was introduced in 1990, around there, then until 2000. Around 10 years people used this AMR technology. After that we had GMR. So, why this technology was used only for a very short time is because of these reasons that I have shown here. So, for example, let us say you make AMR sensor where the permalloy layer thickness is 10 nanometer. So, at 10 nanometer you have like 2% AMR. Now, I want to make the AMR smaller and smaller. Okay. So, as we discussed before, we want to make the bits are smaller. So, we want to go from this dimension to this dimension. So, we need to make the AMR element also thinner. Okay. We want to reduce the shield to shield spacing, because the bit length is going to be reduced. So, when you want to make this closer, AMR element thickness has to be reduced. Okay. So, when AMR element thickness is reduced, okay, you can see when you go from 100 angstrom to 10 angstrom or 10 nanometer to 1 nanometer, you will see that the magnetoresistance is also decreasing, okay, which is not good, because your delta R is small. When the delta R is low, let us say you send some current through the sensor to sense, the voltage change you see also will be low, delta V will be low. Okay. So, because of this reason, people moved away from the AMR technology to GMR technology, then magnetoresistance technology. Okay, let us do some question. There is one tricky question. So, after I ask you that question, I will discuss some more. Okay, I will stop here, there is no timer. Okay, majority of you are right, but still many of you are wrong. Okay, what determines the AMR is the angle between magnetization and current. Okay. It is not the magnetic field versus current, it is the angle between magnetization and current. So, if you remember the slides, I showed you clearly that it is the magnetization and current, angle between magnetization and current. See here again, it is the angle between magnetization and current. Okay, next question. Let us say you want to use a AMR sensor for reading information. Okay, so, this is the AMR sensor you have prepared. Okay. So, now we are not applying any magnetic field. So, in which direction you will keep the magnetization? Okay. Let us say this is 0. I mean, let us say if the magnetization is along this one, let us say we call it 0. If the magnetization is along this direction, we call it 90. So, in which direction you will keep the magnetization, which angle you will keep the magnetization when there is no magnetic field? Okay, that is the question. Okay, there are various answers. So, before I tell you which is the correct answer, let us take imaginary material. Let us take some imaginary material A. Okay. When you measure the resistance or voltage of this material, for example, let us call it resistance as a function of temperature. Okay. Its behavior is like this. Okay. And you want to use this material A as a sensor for measuring temperature. Okay. Which region will you operate? Let us say I say this is the region A, the region B, the region C. Region B, right? Why?
Close to linear.
Yeah. So, because this region is close to linear. Okay. In the other region, your change in resistance is not proportional to temperature. Here you have some kind of linear region. Let us say this is room temperature and you want to measure from say 0 to 100 degrees Celsius, then this region is good, this is good, right. So, in this graph where you see linear region, somewhere here, right, somewhere here is the region, I mean linear region. So, you will usually operate around this center. Okay. So, the correct answer for that question is the theta is 45 degree. So, in the absence of any magnetic field, your magnetization is at 45 degree angle, current is along this direction. So, direction between angle between current and the magnetization is 45 degree in the absence of a magnetic field. Okay, let us say there is some magnetic field going in this direction. So, that magnetic field will force this magnetization to go like this. Okay. So, you will go from this to this. Okay. So, this is now field 0. So, and the magnetic field is up. So, magnetic field pointing up will make this go 90 degree. So, you will see low resistance. Okay. Now, let us say there is a magnetic field pointing down. So, this pointing down magnetic field will rotate this magnetization this way. So, it will make the current and magnetization to be parallel. So, we will go this side. So, remember in magnetic recording we have only two types of magnetic field, right. So, one like you have north pointing up, magnetic field going up, another case south pointing each other, magnetic field going down. So, we have only two fields. So, these two fields either should make the resistance to be low or high. Okay. So, we in the absence of any magnetic field we keep the magnetization at 45 degree, and one type of magnetic field will make it like this, another type of magnetic field will make magnetization to be like this. So, we will go between high and low resistance. Okay. So, the correct answer for that question is 45 degree. Time for tea break. Yeah. So, the next topic, okay, here the correct answer is 45, only 5 of you are right. Okay, so, the next topic will be GMR, then magnetoresistance, we will cover after the tea break. Okay, let us continue. So, before the break I told you that in magnetoresistive sensor, anisotropic magnetoresistive sensor, let us say this is the sensor, we send current in this direction, then the magnetization is at 45 degree in the absence of any magnetic field. Okay. So, the current and the magnetization makes 45 degree angle. So, I told you one type of field will force this magnetization to be perpendicular to the current. Then another type of magnetic field will force the magnetization to be parallel to the current. Okay. So, sometimes the students ask, suppose this field is strong, right, this should be even tilted like this. Okay. So, there is this possibility, if the magnetic field is very strong, it can even force this magnetization to point like this. So, in that case we will be going from low resistance to low resistance, we will not be able to read the high resistance. Okay. That possibility exists if the magnetic field is very high, but in reality the magnetic field produced by the magnetic recording head is magnetic recording media is not very high, around so when you have a disc media, the disc media produces around 200 to 300 worsted kind of magnetic field around. So, this also depends on the height from which you see the magnetic field. So, this magnetic field is not that high to flip this magnetization all the way down. Okay. So, we always go from low resistance to high resistance. Okay. So, only this kind of change happens. So, in the absence of field you are here, in the presence of one field you go this way, in the presence of another field you go this way. So, we go between current parallel to magnetization, current perpendicular to the magnetization. So, we go from high to low resistance and so on. Okay, so, that is how the anisotropic magnetoresistance work. Now, let us move on to the next topic, which is the giant magnetoresistive head. Okay. So, we can call it, this is the magnetoresistive head version 2. Okay, so, many of you might have known Peter Grunberg and Albert Fert. These two professors discovered the concept of giant magnetoresistance. So, they discovered almost at the same time in late 1980s, and this concept was eventually commercialized in late 1990s. And because of the impact of the giant magnetoresistance in revolutionizing the way we read information. So, I told you, right, YouTube, Facebook, the movies like Avatar, all those won't be possible if we did not have GMR sensors, for example. Okay. So, because of the technological impact of their discovery, they also got Nobel Prize in 2007. Okay. So, the discovery of the GMR happened just at the time when the hard disk industry moved to the AMR sensors. Okay. So, hard disk industry was working on AMR sensors before this was discovered. Then somewhere in 1990s, hard disk industry applied this one. So, this is introduced, hard disk industry introduced this AMR sensors around the same time this discovery becomes, this discovery was observed. Okay. Then hard disk industry started looking at this particular concept and they started working on, then finally around, this happened in 1989, then around 2000 GMR was commercialized. So, before I discuss what is GMR, I also want to give you some flavor of how research works. Quite often you will notice that two scientists come up with same idea at same time. Okay. So, this is very common in science, because like we have conferences, right. So, in conferences there will be some presentation. So, you let us say you go and listen to a certain presentation, that will trigger maybe same idea to two different professors. So, they will go back to their lab and work on that particular concept. Then finally, they also publish the same thing at around same time. Okay. So, this happens quite often in research, and in this particular case in 1980s, this multilayer was a very hot topic. So, a few years ago people were doing graphenes, then even few decades ago like we had nanotechnology and things like that, right. So, in magnetism in the 1980s, multilayers was a hot topic. So, instead of growing one continuous film, people started growing multilayers of cobalt and platinum. So, I introduced this a few days ago when we discussed about interface anisotropic. I told you that we can grow cobalt, platinum, cobalt, platinum like this as a set of multilayers, which gives rise to perpendicular magnetic anisotropy. So, this was a very hot topic, because at that time there was also a concept called magneto-optic recording. Okay. So, people were looking for new materials for magneto-optic recording, and these materials were found to be very useful. Okay. So, when you have this topic, right, so people will obviously look at many different materials. So, instead of cobalt you may have something else, platinum you may have something else. So, one such material was iron and chromium, which both groups, the group of Professor Albert Fett and the group of Professor Peter Grunberg, they were working on this iron chromium iron multilayers at the same time, and they came up with this almost similar observation at same time. Okay. So, now I will show you the discovery of both teams. So, here we are looking at the results from the group of Professor Albert Fett from France. Okay. So, in this case they grow a set of multilayers. So, iron, chromium, iron, like they stack n number of times. Okay. So, that n is 30 here, 30 layers of iron and chromium, 35 in this graph, 60 in this graph. Okay. The thickness of iron is the same, 3 nanometer in all samples. And chromium is different, here is 18 angstrom, here is 12 angstrom, here is 9 angstrom. Okay. So, they have 3 different types of multilayers, and they measure the resistance of this device as a function of magnetic field. Okay. So, what they observe is that the resistance is high when the magnetic field is 0, and if you increase the magnetic field, the resistance drops. Okay. So, for this particular set, the resistance drops to this value. For the second set, the resistance goes to this value. For the third set, where we have 60 bilayers, the resistance drops to even larger value. Okay. So, if you look at this difference, so this is almost like 100% change. The change in the resistance as a function of magnetic field is around 100%. Okay. So, this value is very large. So, I told you in formulae we have anisotropic magnetoresistance, which is around 2%. So, compared to that 2%, this 100% is like very huge. Okay. So, that is why they call it giant magnetoresistance, okay, to show that this value is very large compared to the normal anisotropic magnetoresistance that we have. Okay, so, this is the result they get. Okay. So, many of us get result, but we also should explain it why it happens in a convincing manner. Okay, so, this group as well as the group of Peter Grunberg explained this result, that when you do not apply any magnetic field, you observe high resistance. Okay. This is because at this particular field, the magnetization of the ferromagnetic layer, the two neighboring ferromagnetic layers are anti-parallel. For example, if the magnetization of this layer is pointing towards right, then the magnetization of the neighboring layer is pointing towards left, and so on. Okay. So, if you have 60 layers, so all these layers will have one pointing towards right, one pointing towards left, then right, left, and so on. Okay. So, the neighboring magnetization are anti-parallel in direction in the absence of a magnetic field. Okay. So, this is the situation when the magnetic field is 0. Okay, now, let us say you apply a magnetic field along this direction. What will happen? What will happen? Why everyone is quite. Okay. So, at very large magnetic field, all magnetization will point in the same direction. Okay. So, if H is very large, if the applied field is very large, it will force all the magnetization to be along this direction, and that is what causes this low resistance. Okay. So, they pointed out that when you have magnetization of the neighboring layers are parallel to each other, you have low resistance. When the magnetization of the neighboring layers are anti-parallel to each other, you have high resistance. Okay. So, this is the result from the group of Albert Fert. You will see almost similar result observed by the group of Professor Grunberg. So, here they do not have 60 layers or 30 layers, they just have 3 layers. Okay. 1, 2, 3. So, the ferromagnetic layer is iron, the second ferromagnetic layer also is iron, and the layer in between is chromium. Here again they see similar result. When the magnetic field is 0, resistance is high, and when the magnetic field is large, resistance is low, and again when you apply magnetic field in the other direction and when it is large, you see low resistance. So, in their paper they clearly show what happens. So, at 0 field the two magnetization are anti-parallel, and at very large field they are parallel to each other. Okay. So, all these results indicate that when you have two ferromagnetic layers separated by some spacer, and if the magnetization are parallel, you have low resistance, and if there is magnetization or anti-parallel, you have high resistance. Okay. Both results are similar, only thing is the sample structures are different between the two groups. Okay. Another difference is that this observation was carried out at 4 Kelvin or some low temperature. I do not remember the exact temperature, but somewhere at low temperature, whereas this observation from the Peter Grunberg's group is at 300 Kelvin. Okay. So, So, this is the concept of GIAN magnetoresistance. We will go into the detail of this theory, but basically they explain that when you send electrons through a structure like this. So, you have layers of two different magnetization and the electrons undergo some spin dependent scattering. Because of the spin dependent scattering, you see these different effects. So, when the magnetization are parallel, the spin dependent scattering is less, you have low resistance, and the magnetization or anti-parallel spin dependent scattering is more, you have high resistance. Okay. So, there is some theory to it, which we will discuss tomorrow. So, basically you have majority electron, minority electron, and when the magnetization are parallel, majority electron does not get scattered much, the minority electron gets scattered, and when the two layers are anti-parallel to each other, both majority electron and minority electron get scattered. So, you have high resistance. Again I am using lot of jargon like majority electron, minority electron without defining what they are, but we will learn those things tomorrow. So, today I am just yeah. How do we ensure anti-parallel magnetization in the two ferromagnetic layer when coercivity is field is 0? There is going to be some discussion on this, maybe I will discuss another day. So, I have some slides on synthetic antiferromagnetic coupling, I will discuss that later. So, time being you assume, you take it for granted that if you have two ferromagnetic layers and if you have a suitable spacer layer, some suitable material at suitable thickness, you can form the antiparallel magnetization. Okay. So, later I will explain this in detail. So, time being you take it for granted that we can achieve this at 0 field. Yes.
Sir, is there any case like if we apply the magnetic field, there can be any increase in the resistance, like it is decreasing with the application of the field. Is there any case here like can we increase the resistance?
Increase in the resistance. In this case, for example, this is the ground state. In the absence of field, you have this is the ground state. So, this is going to be the highest resistance state, and if you apply field, you are going to make them parallel. So, you will have lowest resistance state. Increase I have not come across. Yeah. Okay, so, this is basically the concept. We will learn the theory more in detail tomorrow, but just for time being you just put it into your brain that there is some spin dependent scattering of electrons, and this spin dependent scattering is larger for both type of electrons when you have anti-parallel spin. So, you have high resistance. Okay, so, when they are parallel to each other, the scattering is larger for the minority electrons, whereas the majority electron does not get scattered. So, their resistance is low. Okay. So, to understand the GMR based sensor, you just need to know that if the two magnetization are parallel, resistance is low, and if the two magnetization are anti-parallel, resistance is high. Okay. So, for time being you only need to know this one. Okay. All the other things we will discuss tomorrow.
So there is one question from online.
Okay.
In slide 33, it's not mentioned is the send on WhatsApp.
Slide 33.
While magnitude of magnetoresistance decreases, which decrease in the thickness of chromium layer.
Decrease in the thickness of chromium layer.
This is the layer I think
Here in this paper. Here the magnetoresistance is increasing when you reduce chromium. So, here is 18, chromium is 18 angstrom 12 angstrom, 9 angstrom. The magnetoresistance is increasing, right? This difference is increasing when you reduce the chromium thickness. Okay, so why is it? That again brings us to the concept called synthetic antiferromagnetism, which I will discuss another day. Okay. So, when we discuss this, we will understand that. Okay, so just keep this in your mind. So, parallel resistance, the two layers have parallel magnetization, then resistance is low. If the two layers have anti-parallel magnetization, resistance is high. Okay. So, time being, this is all you need to know to understand the GMR sensor. This again we will discuss another day. So, let us discuss some questions.
Sir, in bulk materials also we can achieve this magnetoresistance.
Bulk material, there is something called colossal magnetoresistance, people have reported. In some oxide they have observed colossal magnetoresistance, but that is not very useful. For GIAN magnetoresistance, you need the concept I described. So, you need two layers with anti-parallel magnetization. Okay, many of you are right. So, we need at least 3 layers. So, I told you iron, chromium, iron. So, we need at least 3 layers. Okay. So, 2 is wrong. Okay, next question. Even for this question, there are some wrong answers. So, I do not understand. Very simple question. I kept repeating many times that if the magnetization are parallel, the resistance is low, magnetization anti-parallel, resistance is high. So, it is a very simple question. Okay, next one. Okay, so this is very similar to the question I asked before. So, there is no magnetic field. So, in the absence of magnetic field, how will the two magnetization be? Which angle they will make? Okay, many of you are wrong, but I won't blame you because this is not a easy question. Okay, when we learnt about AMR, right? So, when we learnt about AMR, let us say current parallel to magnetization, current perpendicular to the magnetization. So, this gives rise to low resistance if current is parallel to magnetization, we have high resistance. So, when there is no field, we chose this, okay. We chose the magnetization to be in this position. So, the magnetic field was making them perpendicular or parallel. So, it was swinging around this angle, right. So, this was the mean position. When there is no magnetic field, magnetization was at this angle. So, one type of magnetic field will make it here, or another type of magnetic field will make it here. So, we will swing between high and low resistance. Okay. Now, in this case, when the two layers are parallel, we have low resistance. When the two layers are anti-parallel, we have high resistance. So, what will be the mean position? Yeah, they have to be perpendicular. Okay. So, when there is no magnetic field, these two layers will have perpendicular magnetization. So, one type of magnetic field, let us say this field is along this direction, that will force this magnetization to be parallel. Okay. And if there is magnetic field pointing down, that magnetic field will make it anti-parallel. Okay. So, in the absence of any magnetic field, the default is perpendicular. Oops, sorry. So, the correct angle is perpendicular. So, when there is no magnetic field, the two magnetization are like this. So, one magnetic field will make it parallel, low resistance, another magnetic field will point them anti-parallel, high resistance. Okay, scientists often discover something, but it is always the engineers and the technologists in companies. They make a discovery into a product, usable product. Okay. So, in this case, the GMR observation itself had a lot of problems, but there are few people. This particular technology actually came from IBM mainly. So, these are some people who are behind the successful adoption of GMR concept. Okay. So, this is one technology that became a product within very near future. I mean, just after 10 years of discovery, this was a useful product. Okay. You take graphene for example. Okay. Graphene was discovered somewhere in 2005 or 6. They got Nobel Prize in 2011. Now it's like 20 years. Still there is no great use of graphene yet. Okay. People hype a lot. On the other hand, this is some discovery that became useful within 10 years and it is a $20 billion market. Okay. So, I appreciate this technology a lot. So, this technology uses the discovery, but this group of people, they have to invent some novel methods to overcome some of the problem in the discovery. Okay. So, what are the problems in the discovery? First of all, I told you that the work from the group of Albert Fert happened at 4.2 Kelvin. Okay. So, we are not operating hard disk at 4.2 Kelvin, we are operating hard disk at room temperature or at around 80 degrees Celsius. Okay. And so this is one problem. This observation was at low temperature, and if you look at the result that I showed you before, the change between the high resistance and the low resistance, this happened at around 2 Tesla. Okay. 2 Tesla, you need a very huge electromagnet to produce 2 Tesla. Only then you can observe this high GMR. Okay. Whereas, I told you that in hard disk we are receiving magnetic field of the order of 200 worsted or 300 worsted. So, this field is too large. Okay. So, for about 200 worsted you may see a very small change somewhere here, okay, which is not very useful. Then if you look at the other group's data, Peter Grunberg's data, it is at room temperature, that is good. It is also at low field, very good, but the GMR was not very high, okay, it is low. Okay, so, these are some problems, and the other problem is like you have two ferromagnetic layers. At remnants they are like this. Let us say you apply some magnetic field like this. So, do you know which magnetization will flip in one direction or the other? Yeah. So, in this case this layer will flip, but let us say you have 60 layers of them. Then anyway, in the case of reed sensors, we want to keep one of the layers magnetization to be always fixed, and we want the other layer to change with the applied field. Okay. So, your magnetic field comes from the recording media, and that field is supposed to only change the magnetization direction of this layer. Okay. It is not supposed to change the magnetization direction of this layer. So, we want to keep this magnetization layer fixed. Okay. So, this was not discussed in the GMR discovery. So, the three people that I showed you before, so they came up with a solution to keep this magnetization fixed always. Okay. So, one of the layer magnetization will be fixed all the time, and only this one was either pointing this way or the other way, depending on the applied magnetic field. Okay. So, how to fix the magnetization of one of the layers. So, in the early days people came up with the concept called pseudo spin valve. So, in this case what they do is they choose, they have two ferromagnetic layer. One of the layers had high coercivity, let us say this is ferromagnetic layer 2, it has a high coercivity, and this ferromagnetic layer 1 has a low coercivity. So, when you apply magnetic field, only the ferromagnetic layer 1 will switch, this will be always fixed, and this concept is called a pseudo spin valve. Okay. Then the three people that I showed you earlier, they came up with a concept called spin valve, which uses some of the things that we discussed earlier. So, we discussed about interface anisotropy earlier. So, I told you that when you have a antiferromagnetic layer in the vicinity of ferromagnetic layer, then you can have the hysteresis loop shifted in one particular direction. Okay. So, this one we learned briefly. So, this group of people, they use this concept of exchange bias to fix the magnetization direction of one of the ferromagnetic layers. Okay, let us say now we have one ferromagnetic layer, then let us say chromium here, say iron for example, let us say this is again iron. So, the magnetization direction of this iron layer is always fixed in one direction, but only this is free. So, this magnetization will go either parallel or anti-parallel to this magnetization direction. So, this concept is called a spin wall. Okay. Yes. Huh? Last thing is? Yeah, the one we learnt before, right? Sorry.
Why the pseudo term is used?
Pseudo spin wall, the term, I think it came later. The pseudo spin wall term came later. After, I mean, people first proposed this one, that you can have one layer to have a large coercivity, another layer to have smaller coercivity. So, this does not change the magnetization easily, only this will change. So, this was the first concept people proposed, but the problem is it was difficult to keep this fixed all the time, not that reliable to fix the magnetization. So, then people came up with the next concept. So, this is the first concept called spin wall. Then later when people refer to the other concept, they call it pseudo spin wall. So, when people proposed this, the earlier concept, they did not have a name. Okay. What is your question here?
I did not get what were you trying to
Okay. So, this uses the concept that we learnt before. So, earlier we learnt that if you have a ferromagnetic material in the vicinity of antiferromagnetic material and we have certain recipe. So, once we have that recipe, we know that you will have this hysteresis loop, then there is only one remnant direction, right. So, that let us say that remnant direction is along this one. Okay. Now, let us say on top of this iron, let us say this iron or cobalt whatsoever, on this ferromagnetic layer you deposit some spacer layer and another ferromagnetic layer. So, whenever you use this particular system, the magnetization of this layer is always going to be fixed. Okay. So, we use the term pinned. Okay. I mean, there are many terms people use. So, people use the term pinned, fixed. Okay, so, it will look something like this. So, let us look at this picture. So, you have antiferromagnetic layer, you have a ferromagnetic layer on top, and this magnetization is always pinned to one particular direction because of the exchange bias thing that we learned before. And we have the spacer layer. Now, we have another ferromagnetic layer. So, here you see two arrow direction, basically to represent, if you apply magnetic field along this direction, magnetization will point towards right. If the magnetic field is pointing towards the left, magnetization will point towards the left. Okay, so, this is the spin wall GMR. Okay, so, in this case you fix the magnetization direction of one of the layer using this exchange bias concept, and you have a spacer, and we call this layer as free layer.
So what is the need of the first two layers?
Pardon?
So what is the need for the first two layers, so layer and
Okay, so in GMR, how many layers you need? 3 layers, right? So 1, 2, 3. These 3 layers are the GMR layer. Okay. So you want to keep the magnetization direction of this layer to be fixed at one direction all the time. Okay. So to keep this layer frozen at one direction, we use this antiferromagnetic layer. Okay, so do you remember the lectures about the exchange bias we learned? So if you have a ferromagnetic antiferromagnetic layer, the ferromagnetic layer magnetization is pointed towards one direction. So to achieve that, we introduced this 4th layer. So these are the 3 minimum layers that we discussed earlier, but to freeze this magnetization in one particular direction, we bring the 4th layer. Any other question?
In the absence of field, there will be one remnant state on the bottom 2 layers. But
In the absence of field,
there will be one remnant state.
mm-hmm.
In the presence of field, then that changes.
Okay. So this is the question that I asked before. So let us say the pinned layer, layer 1 is pointing along this direction, the free layer is wait, let me do this way. Okay, let us say this is the magnetization direction of the pinned layer. So it is going to be fixed all the time. Okay, I am not going to change the direction. Free layer is pointing in this direction in the absence of field. So at remnant state, it is like this. So if the free layer sees a magnetic field from the bottom, it will go like this. So you have parallel magnetization, low resistance. When there is no field, again this layer will come back here. And when there is a magnetic field in the down direction, it will be like this, anti-parallel. Okay, so the free layer is always going like this. Any other question? Okay, so in this picture it is even more clear. So here for example, this is the pinned layer. Pinned layer magnetization is pointing in this direction. Free layer magnetization is along this direction in the absence of a field. Okay, you see that they are 90 degree with respect to each other, and if there is a magnetic field along this direction, it will change the magnetization direction of this layer from A to C. Okay, if it goes from A to C, it will be the resistance is here, and if the magnetic field is pointing up, then it will force this magnetization to go from A to B. Going from A to B is here. So you can see the resistance is changing along this line. So this field that I showed you, the down direction or up direction, is coming from the recording media. So we learned that in recording media we have magnetization like this. So let us say this produces up field, this will produce down field. No field here, here again up field. Okay, so depending on how you have oriented your magnets, you will have either up field or down field. So, that is what I mean by this up or down field. So, this field from the recording media will force this magnetization to be going parallel, anti-parallel or parallel. Okay, any more questions? Okay, so yesterday when we discussed the exchange bias, I told you that there is some recipe, okay, but I did not reveal the recipe yet. So, today I will discuss the recipe. Okay, so this is the recipe for how to get exchange bias. Okay, so let us say you do sputtering, for example. So, you take a piece of substrate, you grow antiferromagnetic material at first, then you grow ferromagnetic layer at the next layer. Okay, now you have created an interface of ferromagnetic and antiferromagnetic material. Okay, so you have finished the deposition. Now you do annealing. Annealing means what? Annealing means heating your sample at certain temperature for certain period of time. Okay. So, you anneal this particular stack at certain temperature. So, this temperature is less than the Curie temperature of the ferromagnetic material. So, you know that ferromagnetic material has a Curie temperature and the antiferromagnetic materials have a nil temperature. Okay. So, your temperature, annealing temperature TAN should be more than the nil temperature, but it should be smaller than the Curie temperature of the ferromagnetic layer. For example, let us say the ferromagnetic material has a Curie temperature of 900 degrees Celsius. Oops. And the antiferromagnetic material has a nil temperature of 300 degrees Celsius. Okay. Then you will choose the annealing temperature of around 350 degree Celsius, something like this. Okay. So, now this temperature is more than the nil temperature, this temperature is less than the Curie temperature. So, why we do this? We choose this temperature because we do not want this temperature to affect the ferromagnetic materials property. So, ferromagnet will be still ferromagnet below this Curie temperature. Okay. So, at this 350 degrees Celsius, ferromagnetic material remains ferromagnetic because we are far away from the Curie temperature, but 350 degrees Celsius is more than the nil temperature of antiferromagnetic material. So, at this temperature antiferromagnetic material will be what? Paramagnetic. Okay. So, above the nil temperature antiferromagnetic material will be paramagnetic. Okay. So, now we are annealing this sample, then we apply certain magnetic field. Okay. Let us say we apply magnetic field along this direction. Okay, your ferromagnetic moments will point along your applied field direction. Okay, now we start cooling the sample. Okay, we bring let us say we cool down to room temperature, we switch off the heating. Okay. So, the sample is slowly coming back. So, the sample goes from 350 degree Celsius to 25 degree Celsius. Let us say when you cool, the sample goes to around 300 degree Celsius. what will happen? The antiferromagnetic material which was in the paramagnetic state. So, when we are annealing, the magnetic moments of the antiferromagnetic atoms are fluctuating, but once you cool down to temperature below 300 degree Celsius, the antiferromagnetic order will kick in. Okay. So, when that order kicks in, the spins of the antiferromagnetic material which are near this ferromagnetic layer will align parallelly. Okay. So, if these spins are like this, the neighboring spins will be like this and so on. Okay. So, after you cool down to room temperature and finally, you will get this. Okay. So, this is for the case where the magnetic field is applied along this direction. So, if I plot the hysteresis loop of this sample, how will it look like? Let us say magnetic field in this direction represent this quadrant, magnetic field pointing left is in this quadrant. So, I have two graphs A and B. So, which graph matches this? Which A, I mean this one corresponds to the hysteresis loop A or B? Which one? A. Okay. No, it is A. Okay. Because your remnant magnetization is pointing along this direction. Okay. Your applied field is along this direction, remnant magnetization is pointing along this direction, which is this case. Okay. Suppose during this whole thing, whole process, I anneal in the presence of a magnetic field, apply in this direction. Okay, then I cool down, then finally my spins will be frozen in this direction. Okay. So, that will lead to B. Okay, so, the hysteresis loop for B will be like this. Okay, so, this is how we pin the magnetization of the ferromagnetic layer. So, once you do this one, this layer is called pinned layer, because the magnetization of this layer is going to be always pinned to one particular direction, either pointing towards right or left. Okay, so there, yeah. The shape will be like this. I mean. The hysteresis loop will be more or less like this. Yes. Okay, let me show you another case, for example. Is there exchange bias here? Yes. Okay. So, here also we have exchange bias. The center of this is shifted by certain distance, but here we do not have the unidirectional anisotropy. Okay. So, here only one direction, the remanence is only one direction, here the remanence is only one direction, but here we still have two direction. The problem here is that the exchange bias field is smaller than the coercivity of the sample. Okay. So, in this case, for example, your coercivity is only this much and the exchange bias is large. Okay, exchange bias is so big, coercivity is small. So, you will see a clear shift. Here again coercivity is only this small, at exchange bias is large. So, you will see a clear shift. In this case coercivity is large, okay. Coercivity is large, your exchange bias is small. Okay. When the exchange bias is smaller than coercivity, you will have this shift, but you will not have the unidirectional anisotropy. Only in this case we will say it is unidirectional. So, when exchange bias is more than coercivity, only then we have the unidirectional anisotropy. Okay. So, in this case you will not get, quite often this is useless. Okay. So, practical application this is useless. So, you have to either increase the exchange bias or you have to reduce the coercivity, so that you can observe this. Okay, so, you can choose the various type of antiferromagnetic materials like iridium manganese, iron manganese, nickel manganese. So, there are many types of antiferromagnetic materials, but mostly for industrial applications people use iridium manganese with some chromium substitution, a little bit of chromium they add to improve the corrosion performance, because some materials have very large anneal temperature. So, if you want to anneal, you need to anneal at a very high temperature. So, they are useless, and yeah, they look at various parameters, and this material also is good for corrosion. And you want this to be thinner. Okay. So, because of various such reasons, this is the most favorite material for exchange bias. Okay, when you fabricate a GMR head, you can design a GMR head in two configuration. So, in one case the current will flow parallel to the film direction. For example, you look at this picture, right, the current will flow in this direction. So, this is the film plane. So, current will flow parallel to the film plane, that is called current in plane configuration. So, if you look at this picture, so here for example, we have one ferromagnetic layer, spacer, another ferromagnetic layer, antiferromagnetic layer, and so on. So, you notice that the current is flowing parallel to the layers. Okay. So, it is flowing this way. So, this is called current in plane configuration. So, in this case we need some insulators. Okay. So, this is one insulator, and this is another insulator. Why do we use this insulator? Because we are using these shields. You remember I introduced this shield before. So, these shields are like pomalloy or some kind of ferromagnetic material, which are also metals. Okay. So, these are metallic materials. So, when you send current through the GMR device, if you do not have this insulator, current will also flow through this shield, okay. Then you cannot sense the information. Okay. So, to make sure that the current flows only through the GMR device, not through the shield, people use the insulators. Okay. Exchange interaction length.
What decides the critical thickness for the FM?
I am not sure about the exchange interaction length, but if you make the ferromagnetic layer to be thinner than certain thickness, you will not observe the exchange bias. Okay. So, your exchange bias will become smaller than the coercivity of the ferromagnetic material, which is useless. Okay. So, you want to achieve certain exchange bias, which is possible only for certain critical thickness and above. So, if you make the AFM material too thin, you cannot achieve high exchange bias. So, this is a practical reason. Okay, so, this thing shows exactly what is happening. So, you have magnetization of the recording media, they generate magnetic field. So, this magnetic field is making the free layer magnetization to go parallel or anti-parallel to the reference layer. So, you have low and high resistance, and this is how the GMR is designed. So, you have GMR various layers here. So, the current flows parallel to the layer, and this is called current in plane configuration. So, this configuration was working for a few years, but later people went on to another configuration. So, these were some of the disadvantages. Okay. So, you need an insulator. So, if you have an insulator, you are increasing the shield to shield spacing. So, if you look at this picture, because this insulating layer thickness, the thickness between the distance between the shield to shield is larger. Okay. So, this is one of the main disadvantages of the current in plane device. So, because those reasons, people came up with the GMR in current perpendicular to the plane configuration. So, here the plane means like you have one layer, one ferromagnetic layer, spacer, another ferromagnetic layer, antiferromagnetic layer, and so on. So, you have planes. So, current is now flowing perpendicular to the plane. So, that is called CPP configuration. So, here you do not need insulator. So, this is a metal contact, this is another metal contact. So, you are sending current through the metal, through the GMR and taking out that way. Okay. So, here you do not need insulating layer. So, the shield to shield spacing can be reduced. Okay. So, people use CIP first, then they transition to CPP, current perpendicular to plane configuration. Okay, let us do some question now. Okay, I am totally disappointed with this answer. Okay, the loop B is very symmetric. Okay, there is no reason to say that it has exchange bias. Loop A has shifted. Okay, so it has shift. So there is exchange bias. So in this case, the exchange bias is smaller than the coercivity. Okay, that is why exchange bias is smaller than coercivity. That is why you do not see the unidirectional anisotropy.
Still, still the pinning will be there, no?
Yeah, pinning is there. Yes.
So we can apply in spin walls, right? Spin wall devices.
No. In pinwall, I mean in spin wall, you want to where is the pen? Okay. So in spin wall, you want to keep the magnetization of this layer always in one direction. Okay, you do not want this to be either this or this. No, we do not want that. We want this to be fixed in one direction all the time. So we do not want this loop. So in this case, you have both direction, right? So it can be this or this. We do not want that. We want only the case like this. Okay. So, okay, type in your answer. Okay, most of you have written current in plane and it is correct. Next one. Okay, most of you have written current perpendicular to plane, which is correct. I don't know what is this. Okay, so I told you that CIP was used first, CPP came later. So you might wonder why not CPP from beginning? Why we should use CIP for some time, then why we should shift to CPP later? That is because this CPP configuration has its advantages only when you shrink the device size. Okay. So, we shrink the device size when we go towards higher and higher density. Okay. So, when your device size is larger, CPP does not have advantage, because the resistance of this device will be very low. Okay. So, you look at this one, when the diameter of the GMR device is around 300 nanometer for example, the resistance of this whole device is so low that the high resistance and low resistance will be too small to detect. On the other hand, when you go down to say smaller sizes 50 nanometer or something like that, now your resistance is around 10 ohms. So, the swing between the high and low resistance will be reasonable enough to detect. So, for very large device sizes, this configuration is not good. That is why people use current in plane, but once we go towards high density smaller devices, CPP becomes useful. Okay, this one I do not want to teach today. So, we have a few minutes, maybe we can ask question. Any question? Or is there anything that you did not understand, you want me to explain again? Yeah.
In the current in-plane configuration, so if we are not going from the fixed layer to the free, the current is not passing from the fixed layer to the free layer, then how are we
Okay.
sensing this PMR?
Yeah, thank you for asking this question. So, if you remember when I was talking about the first few slides, I told you that the electrons are not flowing like this, they go like this, right. So, even if there is no electric field, they are going around with a mean free path of around 10 nanometer, but if there is a electric field, they are going around like this. Okay. So, I told you that the mean free path is around 10 nanometer. Okay. So, now your GMR layers are, for example, your fixed layer may be say 5 nanometer, the spacer layer may be 2 nanometer, is another 3 nanometer. So, the electrons are not flowing through one layer. So, they are still going around like this. So, they go to all the layers before they go from one side of the device to the other side, they will go through both layers. Any other questions? Anything that you did not understand or you want me to repeat, because at that time it was too fast or too difficult?
So, with that pseudo spin-on structure where they do not use any thinning layer, but two different layers with different coercivity, was that practically used or just experiment?
No, it was a proposal. Yeah, yeah. So, let us say 1989 for example, let us say people 1989 was the discovery of GMR. Then people realized that when you have two layers, you do not know which layer will flip. So, they want to fix one layer. Then somewhere in 1993, people proposed the pseudo spin wall. So, by using different coercivity, you can fix one layer magnetization. But the spin wall concept came later, maybe 1995 or something like that. At that time, I was not following the spin wall closely, but I remember hearing spin wall somewhere between 1995 to 1997, somewhere there. So, this came slightly later than this. And also you know that this one came from university. So, university people do not bother, when they have some idea they will immediately publish, whereas this spin valve concept came from IBM. Okay, so, when people are working on some concept in industry and when they find it useful, usually they will file a patent first, and they may not publish in conferences. So, it will be hidden for many years until they decide, okay, we can publish now. Okay. So, we do not know when this was conceptualized in the company, but so I do not know which is first. So, maybe this came first, but people did not know. Yeah.
So this spin valve like MR loop would be observed in some magnite also, bulk materials. How can that be there?
You mean the exchange bias?
Spin valve like MR.
Spin valve like MR, what do you mean by spin valve like MR?
Some MR will decrease but don't go to its initial position.
Can you come and draw? You come.
There was one slide where
Okay.
this pseudo spin valve was. This one.
This one,
What's this bottom MR was?
this one. Okay. So, you measure MR as a function of field, you see something like this, is it?
Some magnite or martensite usual systems like MR source
Mm. So, it is a single material,
polycrystalline bulk.
polycrystalline bulk.
That may not be because of the scale, right?
I do not know, maybe. Have you heard about colossal magnetoresistance? Maybe you can read some papers to understand whether this is similar to this. So, colossal magnetoresistance also is observed in bulk material. So, some oxides, they give rise to this CMR. I do not know the working principle.
It is related to magnitude of magnetoresistance.
I do not know the principle of CMR. I have never studied that. To online question, okay.
The first is will the defects caused by fabrication cause the significant change in the GMR?
So, defects will increase the resistance. Okay, so, when your resistance get higher and higher, the relative change may not be good. Okay, so, usually the industry, they will try to achieve some number called RA. So, it is called resistance area product, resistance area product. Okay. So, they want to tune this resistance area product to certain value, and if you have defects, the resistance will increase. So, your RA will be increased. So, it is not good, it is not desirable. Then what is the other question?
One more question, sir, here is that in the initial slides,
Mhm.
in the GMR case, if we are decreasing the chromium layer thickness, why the MR is increasing? What is the reason for it?
Okay, that one I told you that we are going to discuss that in synthetic antiferromagnetism. So, let them wait until then.
Why we want CPB? Why we want to move from CIP to CPB?
Okay, so I told you that in CIP, in the case of current in plane, you need to introduce an insulating layer. So, this insulating layer comes between two shields. Let us say you have one shield here, another shield here. So, in between these two shields you have the insulating layer, then here is your GMR sensor. Okay. So, the insulating layer adds to the shield to shield spacing. So, a few minutes ago today we learned that this shielding, this shield to shield spacing has to be low. I mean, when we are talking about high density, this spacing has to be low. Okay. So, insulating layer increases the spacing, which is not good. Okay. So, this is the main problem of CIP. So, CIP means we are sending current through the plane, CPP means we are sending current perpendicular to the plane.
One more question.
Mm-hmm.
In thin film vacuum structures, why CPP magnitude is higher than CIP?
Why CPP magnitude is higher than AP? You mean this one? I really don't know. So, these are some prediction people did. I have no idea why. Okay. So, we can stop here then. Thank you. See you tomorrow.